Hi, my name is Joshua Hare. I'm a senior electrical engineering major, and today I'll be explaining the model of a DC motor. But first I'd like to say that this is very important to me because for my senior design project, I'll be designing and building a tracking robotic cart with my teammates Will Henson and Jacob Reingans. This robotic cart will utilize two 12-volt DC motors, so it is very important for me to know and understand how the motor should work for this project. Now I'd like to talk to you a little about a DC motor and show you a few of the important components of a DC motor. A DC motor is any class of electrical machine that converts DC or direct current into rotational mechanical power. The advantages of a DC motor are its high torque, speed controllability, and portability. This is very important because of the advantages of high torque as well as portability. It makes these small motors very useful. Most common DC motors are about 5 horsepower, and they are generally brushed DC motors. DC motors that do not have these brushes will instead have electronics in place that will switch the current to each coil on and off. A simple DC motor has a stationary set of magnets shown here, and an armature with one or more windings of insulated wire wrapped around a soft iron core that concentrates the magnetic field, and that is shown here. The windings usually have multiple turns around the core, and in large motors there can be several parallel current paths. The ends of the wire winding are connected to a commutator, shown here. The commutator allows each armature coil to be energized in turn and connects the rotating coils with the external power supply through the brushes here. Shown here is the block diagram as well as the transfer function. Of a DC motor. The controller shown in this part of the block diagram sends an input to the transfer function. Once the transfer function receives the input from the controller, it'll output a response. And here is the design that we're going to be using to model a DC motor. Our design is going to include a settling time less than 2 seconds, an overshoot less than 5%, and a steady state error less than 1%. An excerpt of our MATLAB code showed here shows a few of our variables that are just physical parameters to run the code. This is the open loop response of a DC motor, and as you can see, this isn't a very good response, so we'll be using the root locus and the design stated earlier to get a better response. So here's our root locus designed with a gain on our compensator of about 16, and as you can see, our open loop response over here is a little better but not quite where we need it to be. So in order to get this steady state error to less than about 1% in our open loop response, we'll need to at least double this gain. So here we doubled the gain to approximately 34, and as you can see, our open loop response is much better and is within the design specifications we stated earlier. So as you can see, using the root locus, it takes a bit of trial and error to receive good results, but overall it's easy to use, and if designed right, it will give you the correct specifications that you need. If you have any questions, feel free to email me, and thank you for your time.